Hello everybody, and welcome to the beginning of section 5.6. We're looking at page 22 in the workbook. And before we dive into this section, I want to start with just a motivating example here. So in this space above, suppose that we wanted to calculate the integral from 0 to 1 of the function e to the negative x squared. Okay, graphically, that integral represents an area. I'm just going to try to draw that as best as I can. The function e to the negative x squared kind of has this sort of a shape to it. And so the area that we'd be trying to find is this area that I'm shading here. Okay, now, why might we want to do that? Well, there's something special about the function e to the negative x squared. If any of you have ever maybe taken a probability or a statistics class, you might know that this kind of a function comes up when you talk about probability distributions. So for example, if you wanted to solve a problem like how likely is it that if we randomly selected a person from the United States population, what is the probability that their height is going to be between 5'10" and 6'2" or something like that? You can figure out the answer to a question like that by integrating a function similar to the one that we have here. Okay, there's only one problem. If you try to calculate this integral, you discover that e to the negative x squared is not a function that you can find an elementary antiderivative for. So this answer, or this integral, it's not possible to find an exact answer. As simple as that function looks, e to the negative x squared, it's not possible to find an elementary antiderivative, so we don't have any hope of calculating this exactly using any of the integration techniques that we've talked about. So the question is, what do we do then to find this area? Well, that's where numerical integration comes in. That term, the meaning of that term is approximate integration. It gives us a way to take an integral like this that we can't do exactly and find an approximate value of it. Okay, so a lot of you might go on to take a course called Numerical Analysis, and you will go a lot more deeply into this topic of numerical integration than we do here. In this course, we're just going to introduce a couple of basic ways to do this. Okay, so let's start with the first one. It's called the Trapezoid Rule, and basically, it is going to give us a way to estimate the area under a curve using trapezoids. Let's look at the picture over to the right here. So we've got a function f of x. Imagine that we want to estimate the area under that function from a to b. So what we're going to do is to chop it up into n pieces, okay, and kind of label these partition points x0, x1, x2 as we go left to right. And then what we're going to do is to, at each of those partition points, just draw in the function value and draw in a bunch of trapezoids by kind of playing connect the dots here. Okay. And the idea is, if we could figure out the areas of these trapezoids that we're drawing in and add them all up, it would give us an estimate of the area under the curve. Okay, I'm going to label these trapezoids with their areas. So A1 through AN just represents the area of these trapezoids that we've drawn in. Okay, so what we want to do is to write down a formula for the area of each of those trapezoids one by one, starting with A1. Okay, well, turns out that there are geometric formulas for finding the area of the trapezoid. What we need, though, to do before we can do that is to think about some of the pieces here. So I'm going to let delta x represent the width of one subdivision. That just represents the width of one of our trapezoids. And we'll assume that we've divided our region into n pieces. Turns out that if you make those two assumptions, you can find the area of the first trapezoid like this. Okay, and again, I'm looking back in a geometry textbook and just writing down the formula for the area of a trapezoid. If you're wondering where the f of x naught and f of x1 come from, they're actually the values of our function at x0 and x1. They're these two heights that we have here. So we're taking the width of our trapezoid over 2, multiplying that by the sum of the two heights. Okay, and then kind of trusting our geometry book that that's how we find the area of that first trapezoid. Okay, A2, similar idea, but now we're jumping over to the second trapezoid, and its width is still delta x, so we're going to get delta x over 2, and then the only thing that's different is that the heights on either side go with the points x1 and x2, and so we're going to get f of x1 plus f of x2. And this pattern continues until we get to the very last trapezoid, and its area AN is going to be delta x over 2 times f of xn minus 1 plus f of xn. Okay, I'm going to throw in one note here. When we get around to using this formula, it'll be useful to know that delta x, the width of one of those trapezoids, is actually b minus a over n, because of the fact that we're taking the interval between a and b and we're chopping it into n pieces. That's kind of the logic of where that comes from. Okay, so let's clear away a little clutter here. Okay, and now we are ready to write down a formula for the approximation using the trapezoid rule. Okay, so we're looking here. The Tn that you see is in words as saying the trapezoid rule using n trapezoids. That equals an approximation of the area under our curve, the integral. And to get the area approximation, we're just going to add up the area of those n trapezoids one by one. Okay, and now we're going to need to do a little algebra. We actually have to take and add up all of these formulas one by one. And one thing you might notice is that with all of those formulas, there's a delta x over 2 in front of everything. So what I'd like to do is to factor that delta x over 2 out, and then just multiply it by the sum of all of the pieces inside one by one. Okay, so we're going to take f of x0 plus f of x1. That takes care of the first trapezoid. Plus f of x1 plus f of x2. There's the second one. Okay, we keep going. Okay, and eventually we come to f of xn minus 1 plus f of xn. Sorry for writing small on you here. Okay, hopefully you can read that. And let's take a look at what we've got now. Okay, if you look inside of this big set of brackets here, you might notice that there are some terms that are repeated. For example, there are two f of x1s, there are two f of x2s, and so if we rewrite all of this, it looks like delta x over 2 times f of x0 plus 2 f of x1, because there were two of those, plus 2 f of x2. And if you continue, which terms are going to have 2's in front of them? If you think about it, every term is going to appear twice except for the very first one and the very last one. Those two only get listed once. So if we continue with this formula, we're going to get 2's in front of everything up to the second to the last term, and then the last term is just going to have a 1 in front of it. Okay, and I'm going to ask you to go ahead and box in this last formula. That's what we want to remember. That's the formula that's going to give us the approximation for the integral using these trapezoids. Okay, and in a future video, we'll do an example to illustrate how we would use that formula.